Constraint optimization. Okay. So let us actually start with a slightly notice that here I'm trying to minimize my function subject to these inequalities, right? Let us first start with the classical Lagrangian case. This goes back to Monsieur Lagrange, who was actually Italian, but never mind. Despite the French name, he lived in France, and they Frenchified his name. But he invented he had a very clever idea, which we're going to see shortly. But it was only for solving optimization problems subject to equality constraints. Okay? So let us first solve the equality case, and this is something that, a lot of people, not in computer science, but in things like double E and, whatnot, they see this in college, right? The method of Lagrange multipliers. But then we're going to need more than that. We're going to need to deal with inequalities. So let's do the equalities first, and then go on to inequalities. Okay? So this is the problem that we have to solve. We want to minimize some function f of w subject to a set of constraints hi of w is equal to 0. Right? Hi is any function. I just have a whole bunch of these, right? Each one of them is a constraint, and I can always express the constraint as some function being equal to 0. Right? Notice, for example, that there's a case of this that you probably already know, which is what? What's a very common special case of this? Is when the constraints have what form, and the function has what form. Let's suppose that the constraints are all linear, right? Simplest case is always the linear case, right? If the constraints are all linear and the function that I'm trying to optimize is linear, what is this? Linear programming, right? So linear programming is a set of techniques for solving a special case of this. But we're going to be interested in a more general case in particular, right? We're actually going to have linear constraints, but the function that we're optimizing, you will notice, is actually quadratic. Right? So we can't use linear programming. This is actually what's called quadratic programming. Okay? Or at least the particular case that's going to be relevant for us. Okay? So, how do we solve this problem? Right? Well, here's one thing that might come to mind, right? Well, these are equations, right? They basically mean that, my space of solutions is smaller, right? So if I have these equations, let me take some of my variables, right, express them as function of the others, by solving the equations, right? Let's suppose that I had a problem over, variables x1 and x2, right? If I have a constraint over them, right, that means that I'm no longer on the plane, I'm on a straight line, right? So I can express x1 as, ax2 plus b, right? And now I just have a problem in x1, right? So you could, naively say, well, the constraint optimization problem is not a big deal, right? I find expressions for some of the variables as a function of the others based on the constraints, and then I just solve an unconstrained optimization problem, right? Did everybody get this idea? The problem with this is that it gets very complicated very quickly, right? Especially since these equations could be nonlinear and whatnot, right? So most of the time, this is not a very good idea. You could try it, but most of the time, it's going to be very difficult. Unfortunately, Monsieur Lagrange had a much better idea. So let's look at what that idea is. And in fact, let's illustrate this with a nice little example on the plane. Nothing like a simple example to hopefully make things clear. Let's suppose for just a moment that I just want to minimize the function x1 squared plus x2 squared. Okay, with no constraints. Okay, just in 2 dimensions. Okay, let's draw a little diagram of that here. Okay, so here's x1, and here's x2, right? And let me draw contours of constant value of the function, right? What are they going to be? What's their shape going to be? They're going to be circles, right? So it's going to be a bunch of circles like this, right? So this, for example, is x1 plus x1 squared plus x2 squared equals to 1, and then this is equals to 2, and equal to 3, right? And so forth, okay? So what is the solution to this problem? What is the x1, x2 that minimizes x1 squared plus x2 squared? Just by looking at it. 0, 0, right? The solution is the origin, right? I said I was going to make it simple. Okay. Now this problem can be solved by inspection, as they say, right? But in general, how do you solve problems like this? It's like we saw when we were looking at neural networks, right? Is by forming the gradient, right? The derivative of the function with respect to x1 and x2, right? And then equating to 0 and solving, right? In this case, it's very simple, right? Because the derivative of x1 is just 2x1, right? And, then I equate that to 0, and I get x1 equals 0, right? So this unconstrained optimization problem is as easy as they get, right? But now let's look at the constraint case, right? So let's say that my constraints are that x1 and x2 have to be such that x1 plus x2 is equal to 1, right? So this is my constraint. And what this constraint means is that I can't just go, optimize this function any way that I want. I have to stay on that line. That's the key, right? Notice the line is a lower dimensional space compared to the plane, right? I've lost degrees of freedom. In particular, let's suppose that, this was x1 over here, and this was 1.5 and so on, right? So let me try to draw this, right? Here's my line, right? Forgive my poor drawing skills, right? So, but this here is x2 equal to 1, and this here is x1 equal to 1, okay? So the problem here is that I'm trying to minimize this function that is given by these contours, right? While staying on that line, okay? So now I can't wander all over the plane anymore. I have to stay on this line. Basically, all I can do is go up and down this line, okay? So now, where is the minimum going to be, roughly speaking?
45 degrees.
Yeah, it's going to be here, right? You see why? The way to think about this is like picture yourself on that line, right? Think of this as like it's like a road. You can only go on that road, and there's a function, right? The function is defined on the road and all its surroundings, right? Picture like one of these straight roads in a completely flat desert, like you often see in Hollywood movies, right? Somewhere in Arizona or something, right? And you go down that road, right? And this function has values all over the map, right? And maybe its minimum is over there, but you can't get off the road. You have to stay on the road. So all that you can do is drive down that road until you find the minimum that's on the road and stop there, right? So what happens when you do that, right? What I'm doing is I'm going along here, right? Well, the function is going down, right? You agree? It's going down, it's going down, it's going down. Now is it going down or up? Now it has started to go up, right? So my problem is that I want to find this point over here. Right? That's the problem. I'm no longer looking for this point, I'm looking for this point. And so the question for us is, how do we find that point? Right? Well, let's see, what is it that characterizes this point? Right? If you think about it, what characterizes, this is really the key idea behind Lagrange multipliers, is before we get into the math, is what characterizes this point, if you think about it, is that the gradient of the function is perpendicular to my constraint line at that point, right? You see why? Right? Remember, this function is defined in the whole plane, right? And it has a gradient everywhere, right? What happens if the gradient is not perpendicular to the line? It means that it has a component along the line, right? Well, that means that I can keep walking along the line and make my function smaller, right? So it has to be that the point at which I stop is the point at which the gradient of the function is perpendicular to the line. Which means that in order to use gradient descent and keep making the function smaller, I would have to get off the road. But I'm not going to do that. Okay? Everybody see this? Okay, so now here's the next key step, is that how do I get from one to the other? Right? So basically what happens is that I want to find a solution that makes this projection be 0. Right? So if you think about it, what happens is that let's think of the gradient in some, arbitrary position. Like, for example, here, right? The gradient, right, is actually pointing, partly along the line and partly off it, right? You can decompose into this diagonal and perpendicular component, right? Now, if you think about it, I want to get from this to the part that I care about, which is the part that's going along the line, right? And the way I project this gradient onto this gradient is by, I project this line onto this line is by adding a vector in this direction, right? Let me try another color here, right? Is by adding a vector in this direction, right? Adding that vector swings me from a bad direction to a good one, right? And it's when this vector, and I know, this is the key, I know that at the solution, this vector has become 0, okay? So, to put that in math, right? This is where Lagrange had his beautiful idea, right? what's going to happen is that at the solution, so let's call W star my solution, okay? At the solution, now let's do this in many dimensions, right? We will come back to this example shortly and solve it using Lagrange multipliers, but now let's look at the definitions, right? At the solution W star, I'm going to use star to always represent the solution to the constraint optimization problem. The gradient of my function, right, which is now in many dimensions and there's many constraints, right, hi, where I could be 1, 2, 3, 4, 5, right? This gradient, it must lie in the subspace spanned by the gradient with respect to each of the functions, right? It has to be a linear combination of them, right? It has to be in that plane such that it's perpendicular to my constraint surface, okay? This is the key thing. Okay? So, this is what we're looking for, right? So, Lagrange's idea is, well, let us define a new function that we can optimize that will guarantee that that's what we found. So, the whole idea of Lagrange multipliers is very clever. It's like, I'm going to turn a constrained optimization problem into an unconstrained one by adding something to the function. Right? This is a nice thing to have, right? It's much, much easier than doing a lot of complicated equation solving and substituting into the original problem and then getting a very complicated function and trying to optimize that, right? So this is what's called the Lagrangian function. The Lagrangian function, usually denoted by L, is going to be a function of two things. The weights, right, in our case, or the, whatever we're trying to optimize over, right? Plus a new set of variables, the betas, that are the Lagrange multipliers, right? The famous Lagrange multipliers. Usually, lambda is used for Lagrange multipliers, but in support vector machines, people use beta, right? Because we're going to use alpha for something else, and then there's going to be alpha and beta, right? So, and the idea is that by optimizing this new function, we guarantee that we're finding the optimum of the constraint function, okay? So what is the new function? It's just the old function plus a linear combination of the constraint functions, because we know that the solution is in a subspace spanned by these, right? So, right, we're going to have to find the minimum of this function with respect to this and this set of directions, okay? So, another way to look at this, which I do not encourage, but often I think is what people do in practice, is you can just think of this as a very simple recipe, right? Irrespective of sort of like the geometric intuition, the recipe is very, very simple. It's what do you do when you have a constraint optimization problem is you take each of these, multiply it by a beta, add that to the original function, and now just do your good old, unconstrained optimization. Okay? Questions so far? So basically, finally what we're going to solve is this problem, right? I want to find the W star and beta star that make the gradient of the Lagrangian equal to 0. Okay? So this is just the good old unconstrained problem, except it's over, the old and new variables, and the function has this, new term in it. Okay? Questions? Okay, this is still probably, kind of nebulous, so let's continue with our example, right? So let us solve this example using the method of Lagrange multipliers, right? So how does it go? Well, let us first of all form our Lagrangian function, right? So what's our Lagrangian going to be? Well, it's going to start with the original function, right? x1 squared plus x2 squared plus what? Well, first of all, how many constraints are there in this problem? Just one, right? It's this here, right? There's only one h1, right? And remember, the idea is that the constraint has to be in the form something equal to 0, right? So how do I put this in that form? It's going to be what?
Minus 1.
Right, x1 plus x2 minus 1 equal to 0, right? So this is my h, right? So now the recipe, right, is that the Lagrangian, right, I'm going to have the Lagrangian multiplier, let's call it lambda, in keeping with tradition. The Lagrangian multiplier times this, right, gets added to the function, right? So what did the recipe do here, right? Let's go back to our little diagram. Like, what this condition doing here is encoding the fact that my gradient is going to have to be perpendicular to this surface at the solution. Surface, which in this case is just a straight line. Okay? So that's what that's doing. Okay? Right, this thing is going to ensure that I find this solution and not this solution. Okay? All right. So now this is my Lagrangian, right? And now we can just do unconstrained optimization, right? So but now remember, now I have three variables, right, that I'm dealing with, right? So I need to find the zero of the gradient with respect to all three of them, right? So what's the derivative of L with respect to x1?
2x1 plus lambda.
2x1 plus lambda. You agree? Right? There's 2 coming from the 2x1 comes from the quadratic term, but now there's the lambda, right? That's why this is going to be different, right? And we want this to be equal to 0, right? Remember? This is how I find the minimum, is we equate all components of the gradient to 0, right? Just as we were doing for, perceptron, right? So 2x1 plus lambda has to be equal to 0. Same thing for x2, right? This thing is completely, symmetric in x1 and x2, right? 2x2 plus lambda is equal to 0, right? Right, this is pretty intuitive so far, right? And now what is the final condition, right? Is that the derivative of L with respect to lambda also has to be 0, right? What is the derivative of L with respect to lambda?
x1 plus x2 minus 1.
x1 plus x2 minus 1, right? It's just this expression that we had here, right? So, surprise, surprise, right? This is making a lot of sense, right? What zeroing out the derivative of the objective function with respect to the Lagrange multiplier does is just, restates the constraint that we started out with. Okay? Very good. And now, what we have here is a system of equations, right? We can solve that system of equations. It's clearly, this is not a very hard one, right? In general, you could be solving monstrous systems, but this one here, we can do by eye, right? And what do we get? We get that, x1 and x2 are both equal to a half, right? Which, if my drawing was better, would also be, obvious from looking at the graph, right? So if you think about the fact that you're at 1, 0 here, right? And sorry, you're at 0, 1 here, and you're at 1, 0 here, right? It makes sense that this is at half, half, okay? So that's my solution. And by the way, lambda is equal to minus 1. But we don't care. Actually, we don't care about lambda, so in fact, one of the ways of solving this, right, is we get rid of the lambdas, and then we just solve the resulting equation in the resulting problem in the x's. In fact, Lagrange multipliers are sometimes called silent multipliers, because they're a little bit like the dummy variables in summations and whatnot. We don't care about them. On the other hand, and in complete contradiction with what I just said, sometimes the lambdas are exactly what we want to focus on, right? In fact, when it comes to solving this problem, you have two choices. Get rid of the lambdas and solve it over x. This is often called the primal problem. But you can also do the opposite. You can get rid of the x's and solve the problem with the lambdas. And this is called the dual problem. People in optimization are always going on about primal and dual, right? That's what the dual is. The problem is the same, but you're solving it over the so-called dual variables, which are the Lagrange multipliers that you've introduced. Okay? And sometimes that's easier. In particular, for support vector machines, that's going to be easier. And also, it's going to have a very intuitive meaning, right? So what would that mean here, right? What that would mean here is that I would have to express x1 and x2 as functions of lambda, right? Which is easy, right? What is x1 as a function of lambda? If 2x1 plus lambda is equal to 0, then x1 is equal to minus lambda over 2, right? Everybody agree? And the same thing for x2, right? Right? And now I can take these guys, right, and replace them into my Lagrangian, right? And then I have a Lagrangian that's only over lambda. In this case, it's actually clear that it's going to be easier because, it's going to be a function of only one variable and so on and so forth, right? So what is the Lagrangian that I get when I do this replacement? I get minus, to skip a couple steps of this math, right? I get, that the new L, right, as a function of lambda is minus lambda squared minus lambda. Okay? And now, right, this is just now an unconstrained optimization problem only over lambda. This is my dual. Okay? And now I solve it. I equate its derivative to 0, right? So what that means that, minus lambda minus 1 is equal to 0, right? You agree? Right? The derivative of minus lambda squared over 2 is 1, right? So this means that what? That lambda is equal to minus 1, right? And then from that, I immediately get that x1 and x2 are a half, because I knew what they are as a function of lambda. So I can solve this in the primal, and I can solve it in the dual. Okay? Question? We've actually illustrated a lot of stuff about constraint optimization in just these, 10-15 minutes. Okay? Everybody happy, or anybody have doubts about constraint optimization? By the way, at the end of the day, right, you learn these, Lagrange multiplier things in school, but that's, at the end of the day, your solver, right, is going to do, its thing, right? And often it does not involve Lagrange multipliers. Nevertheless, the Lagrange multipliers are very useful for formulating the problem. And for things like, the solver is probably not going to be doing things the way we've done in this little example here, right? We will see in just a second what we might do for support vector machines. But nevertheless, this notion that you could go to this dual problem is potentially very powerful. Because in some cases, the dual problem is easy to formulate and it's much, much easier to solve. Okay? So always bear that in mind. Okay? Any questions? All right. Very good. So, that was our introduction to constraint optimization. And at this level of abstraction, we now have what we need to go forward, right? We know how to solve these constraint optimization problems, right? What does this mean for support vector machines? Okay, remember, the reason we went into this is that we wanted to solve this problem, right? Minimizing the norm of the weight vector subject to all the margins being at least 1. Okay, so what does constraint optimization and Lagrange multipliers and Primal do? What does all of that mean applied to support vector machines? It actually means something very interesting. Here's what happens. Remember, my primal problem is over W, right, which are feature weights, right? Remember, this is a glorified perceptron with a kernel instead of a dot product, but these are weights on the features, right? So this is the primal problem that I'm trying to solve, right? I'm trying to find the optimal weights for the features, but wait, isn't the support vector machine weights over the examples? Yes. You know where those weights over the examples come from? They're the dual variables. Aha. Again, I'm not going to prove that here, but hopefully this, this has some intuitive value, right? What happens in the SVM is that my betas, my Lagrange multipliers, are my instance weights. This is why we can be simultaneously solving this problem of finding optimal weights for the features and optimal weights for the instances, because they're really the primary, they're duals of each other, these two problems. And in particular, it's, you can use, there's both classes of methods, but often for support vector machines, typically people use, the dual formulation. Okay? Questions? So, the feature weights, right, are my, the example weights, right? Those are my dual variables, and just as a preview of what's going to happen, the reason I'm going to wind up with a sparse solution, right, is that a lot of the dual variables are going to be 0. Okay? This is, remember, right? I said that only on a good day, only a small fraction of the examples will be chosen as support vectors, right? In optimization terms, what that means is that when I solve my dual problem, right, that dual problem, the solution to that dual problem is going to have a lot of zeros. A lot of the betas are going to be 0, okay, or alphas, as we see shortly.